All right, let's get going. So last time what we were doing was trying to figure out these limits algebraically, and we ended up trying to find those limits of those piecewise functions, which was a little bit problematic, but hopefully you understand it. So we're kind of done with that now, and we're going to move on to this topic of continuity, and then that'll lead us into the derivative. Now, your homework for tonight will be the 10-3 homework. You don't need to start the 10-4 homework tonight, so just do the 10-3. Tomorrow I will make the video solutions for 10-4. I don't have those done yet, so wait, do I? You know what? I take that back. I do have the videos for 10-4. Yeah, I do. Never mind. But only do the 10-3 tonight, okay? Now, this topic of continuity is actually, it's not, I don't want to say it's not important. The idea of continuity is not that important in terms of what we're going to do in this class, but there is a result of continuity that we need in this class. So the idea itself isn't so important, it's what comes from it that is important, if that makes sense. So let's start with the idea of continuity. I'm going to do it graphically first. I'm going to show you what it looks like, and then we'll talk about what it means by its definition, and then we'll do some examples. So I'm going to put some pictures up here. Let's take a look at, and let me just erase this so I can have more board. I'm going to give you a couple of graphs up here. Let's see if y'all get this or not. A, L, M. Okay. Okay, let's start with those, all right? Okay, so for this first one, we'll just say this example 1, example 2, example 3. So for example 1, does the limit exist at A? No? Okay, why not? Because why? Okay, so is the whole the reason that the limit doesn't exist? They don't go to the same place from both sides. That's why the limit doesn't exist, right? Now, does the limit from the left exist? Yes, what is the limit from the left? L, right? Okay, the limit from the right? M, right? Okay, so the limit does not exist. Overall, it doesn't exist. From the left, it does. From the right, it does. The fact that there's a hole here actually has nothing to do with the limit. So the holes have, you can kind of remember, this is where we're ignoring what's happening at A, and we're looking at left and right only. Okay, how about over here? Does the limit exist at A? No. Does the limit from the left exist? Yes. And what is it? L. Limit from the right exist? What is it? M, sorry. M. Okay, now what is f of A here? What's the function's value? By the way, these are all f, okay? What is the function's value at A here? L. Now, I didn't ask you that here. What's the function's value at A here? Undefined, right? Because there's holes. Now, for this one, does the limit exist? No? Limit from the left? L. From the right? M. What's f of A? N. Okay. So all of these examples here are examples of functions that are not continuous at A. And when you think about continuous, the word continuous, I want you to think about it in terms of like real world. Continuous means, you know, it continues, right? So imagine I'm trying to draw this picture right now. If I were to draw it, at some point I'd have to pick my pencil up off the page, put it down, and then continue to draw it, right? So it's not a nice, smooth, continuous stroke. I actually have to lift, come up, and then keep going. Same with this picture, right? Come here, I draw the dot, pick up my pencil, continue, yes? So none of these are just nice and smooth, continuous stroke. Make sense? All right, so that's your first three. Now let's change this. I'm gonna just erase these. This will be example 4 now. Like that. And let's do like that. And this last one. That. Okay, so how about that one over there? Does the limit exist? Yes, the limit does exist. So I'm going to put that down right here. For this one, the limit as x approaches a of this function equals what? L, right? It equals L. You all right over there? Okay, equals L. If you came in late, I already collected quizzes, and anytime I give you a take-home quiz, it must be turned at the beginning of the class, so make sure you get it up here, all right, if you have the quiz from last time. All right, so the limit exists here, and it's equal to L, right? Okay, what is f of a? What's the function's value at a here? It's undefined. Does this graph seem like it's continuous? If I draw it, will I have to pick my pencil up? So if I'm drawing this, am I allowed to draw a dot there? No, I'm not, right? So like I would actually have to lift my pencil up and go over that and go to the next side, right? The circle is only there as a representation that there's nothing there. I mean, I guess you could say that you could draw it and then draw your circle and never lift your pencil. I get that, but I mean, technically there's a hole. So I should draw, lift up, and then keep going, yes? That is not a continuous stroke, right? Okay. How about over here? Does this limit exist? Yes, the limit as x approaches a of this function is what? L. Okay, how about f of a? It's m, right? F of a is m. So can I draw that without picking up my pencil? No. Finally, we get to this one. Now, does this limit exist? Yes. Limit as x approaches a of f of x, what is it equal to? L. What's f of a? L. So if I draw this, when I get to a, I just put the dot there so I don't need to lift my pencil, and I just keep going, right? This is this one right here, okay? This right here, we would say f is continuous at a, all right? This is the one that is continuous at a. So when you look at these three things I have written down here, can anybody kind of guess as to what the definition of continuity is going to be? What is the condition we're going to have to say something is continuous at a point A? What's that?
It has to be filled in. It has to be filled in like at that point.
Filled in, okay.
F of the limit of x approaching a has to equal.
Oh, okay, so the limit here, right, is L. So the limit needs to exist. And the answer to the limit must match the function's value at that point. You see that? These two are both L. Here, this is L, this is M. See, the limit exists and the function is defined, but they are not the same value. And so we have that little break. Here, the limit exists and the function is undefined. You need basically these two to match each other for it to be continuous. This and this have to match. They don't here, right? And they don't here. but over there they do. These two match. Understand? So that is the definition of continuity, and I'm going to write it down now. Now, while I've got this up here, I'm going to put a different point other than A. How about at B? Look at this picture right here. Is this function continuous at B? Yes, because it's coming in from the right and from the left to the same place, and at B it's defined, right? And you could have done that for any point, right? Any point you wanted to, it would have worked, except what? A, right? So that function right there is continuous everywhere except A. Understand? How about this one? Is this continuous at B? Yes, same principle. Is this one continuous at B? Yes, same principle. Does anyone have any questions over that? Okay. So here's the actual technical definition of continuity. And when I put it up on the board, you'll see why I wanted to draw the pictures first. Just remember, I'm going to leave that one up there. The definition of continuity a function f is said to be continuous at x equals a. I'm going to underline the definition. Okay, we're saying to say something is continuous at a means this. If the limit as x approaches a of the function, right? The limit, this limit right here, this limit has to be equal to what? What does this limit have to be equal to? The actual function's value at a. So this says f of a, and that is it. That's what you need. So if somebody asks you to show that a function is continuous at a, this is what you have to show is true. That the limit exists and that it's equal to the function's value at the point. So it's kind of like looking from the calculus perspective, coming in both directions. Whatever answer we get there must match up with our algebra answer, which is just plugging the value in directly. If we have that happen, we're in business. Questions, comments, concerns, complaints? All right, let's do an example here. We're going to do one visual example, then we're going to get into algebraic examples. Or one graphical, and then we'll do algebraic. All right, so take your time to draw this graph. You don't have to be perfect with it. I don't want you to break out graph paper or anything. But do pay attention to trying to draw it the best you can. 1, 2, 3, 4. So let's say that's 4 units this way. And this is a good example of a problem that I would put on a test, give you a graph, and then ask you a bunch of questions. Bless you. Okay, so there is a graph. There is your XY coordinates. And now I'm going to put a graph in here, and I'll put the graph in blue. I'm going to change that to an open one. Okay, take a second, just make sure you've got that graph. Like I said, again, it doesn't have to be perfect, but everywhere I have a dot, make sure you kind of know where those dots are, those little circles. Give me another 10 seconds. First question, where is f not continuous? And this is the function f, by the way, okay? And let's start seeing who's the lucky ones today. Who's the lucky ones today? Okay, Google. Random number between 1 and 26.
Okay.
I'm giving you time to think about this. Where's Aaron? Aaron Espinosa. All right, if I've already called on you, then let me know. I'm keeping track of it, but just in case I mess up. All right, Aaron. Do you understand what I'm asking you here?
Yeah.
Okay. Can you tell me where the function is not continuous?
The x values, right?
Yes, it's the x values. Which ones?
Right, x equals -3,
Okay, so I'm going to write this down. X equals -3. Where else?
x equals -1,
X equals -1.
and x equals 3.
X equals 3. Okay. Show of hands. How many of you agree with this? Okay, good. This is correct. Good job. So one of your first questions was it was x values, right?
Yes.
Yes, when you're talking about continuity of a function at a point, you're talking about the x values. So what we're saying is, where do we not have continuity? And at -3, so if we move our x value to -3, 1, 2, 3, you can see here, obviously you can't draw this out picking up your pencil, right? You've got this break in the graph. So your limit from the left and the limit from the right, they are not even the same, so the limit doesn't even exist there, right? And then even if it did, it doesn't match up with the function's value. So there's like a catastrophe happening here. Then at -1, same thing. The limit from the left exists, limit from the right exists, the function is defined, however, they don't go to the same place from the left and right. So no go. And then, where did you say 3? Right here? We have a hole, which means the limit exists or no? Does the limit exist at this point? Yes, right? What's breaking down though? What's causing it not to be continuous here? What's the problem? The hole, right? The function is undefined here, right? So those are the 3 places. Good. Any other questions about that? Okay. Part B. Let's see here. I'm going to do part B and part C. Okay, Google. Random number between 1 and 26.
Here are some results from the web.
Random number between 1 and 26.
Coming right up.
So the next person's going to answer part B and C. Derek, you're up. Where's Derek? Right? Are you ready or you want some time? Okay. Looking at the graph here, Derek, what is this asking? You know what this is asking?
Where we approach -1.
From the left, okay? So what is the function doing as you approach -1 from the left? Where is it headed? Okay, can you tell what y value it's headed towards?
-2.
-2? That seem about right? Okay, I agree. Everyone agree with that? Okay. How about this one?
Where does x approach from right to -1?
Okay.
1.
1. Okay, good. So we are looking at -1 approaching from the left. The function was approaching -2. From the right, the function was approaching 1. So those are problems from a few classes ago, right? Those two. This one will be harder. In fact, I'm going to ask for a volunteer on this one. Where is f continuous? Yes, ma'am.
All places?
Yes. So I'm asking you the opposite of this. Don't tell me where f is not continuous. Tell me where f is continuous.
Or does that be?
It has to be an answer that covers everything that you want it to cover.
Okay.
Why don't you verbalize it and I'll help.
Okay, so it's kind of like the domain vector.
Good.
Yeah. So from like negative infinity, I guess, to what is that one? That's
-3? Okay, good. So what she's saying, what's your name again?
Ebony.
Ebony is saying that, look, our graph right here, everywhere over here it's continuous. If you pick any point, it's nice, isn't it? Like you're coming in from the left, right, and it's going to the same point, so I can draw it without picking up my pencil. So I've got continuity over here. The arrow means it keeps doing this. So you're saying everything that way, all the way up to this -3. So we would write that negative infinity to -3 with parentheses around both.
Do you use the U?
The union, good. Union, and now where do you want to go from?
-3 to -1.
Right there, in between here, this little section right here is a nice continuous piece. So we say -3 to -1, parentheses on both again.
And then
Another union,
-1.
-1,
To what is that? 3.
3. It looks like 3, yeah, till 3. So -1 to 3. What's that?
Is that other -1 going to be a bracket?
Ah, very good question. Is this, you're saying on the -1, is that a bracket? When it comes to continuity, when we talk about continuity, you need more than one point. So you need not only what's happening at -1, but you need the numbers next to it. So this is one of those rare times in math where if you leave the bracket off, it's okay. You can put it in or you can take it out, all right? So I normally just leave it out. So just when you're doing this, if you're doing ever asked, where is it continuous, just use parentheses the whole time. Don't ever use brackets, and you'll be safe. Okay, there was one last one. It was 3 forever. Okay, good job, Ebony. So I think part A is an easier question, because it's like, hey, where is it discontinuous? Where is it not continuous? You just list out the 3 points, right? But if you ask the opposite of that, where is it continuous, you've got to somehow represent all the answers that aren't those, right? All right, any questions on that? All right, we're going to do just off this. This is still kind of a review of stuff we've already done, but just want to make sure everyone's up to speed here. Part D. What is the limit as x approaches 3 of the function? And then E, what is the limit as x approaches -3 of the function? So the next person is going to get both of these, and then we'll be done with this and we'll move on. I need to just like download a random number generator app. Random number between 1 and 26. Lucky 15. Oh, we already called on Carlos. So I'll just go down one. Sydney? All right, Sydney. You feel okay with those questions? Feel okay? What do you got? So the limit is x approaches 3 of this function. What are you thinking? Okay, so what are you doing? You're saying like -3 right there? You're right. This is right. So you said you're approaching 3. Here's 3, right? And you're on the function, and your function is approaching -3, right? Now, were you looking? Which side were you looking at? The left? Were you looking at the right at all? Should we look at the right? What do you all think? So because I didn't put plus or minus, that means you have to look both. And luckily, on this particular piece of the function, from the left and from the right, it's headed to the same place. It's headed towards -3. So the answer to this one is -3. Now, Sydney, how do you feel about this one? Okay, undefined. So when you go out to -3, you come in from the left, it's headed somewhere, but you come into the right, it's something different. So whenever that happens with limits, we don't use undefined, we say the other one, does not exist. Remember that? Okay, so that's what we're going to put here. Does not exist, which I put DNE. Now look, if you're taking your test and you put undefined there, I'm just not going to give you full credit. I'll give you like 9 out of 10 points. All right, it'll be still good, but I prefer that you use the proper notation for it. Does not exist. All right, that's it. All right, let's move on. I mean, we're still going to talk about continuity, but let's move on to a different sort of approach without a picture. So I'm going to put a function up here. And we started messing with these functions last class. These were called, what type of functions? Do you remember what? Piecewise. All right. I could draw this. If I wanted to, I could draw this. And I think because it's our first example, I will draw this. But when we do the actual problem here, when I put the question on the board here in a second, we would want to do this problem without a drawing, without a picture. All right, so let's just get an idea of what this looks like. All right, x squared. Are we all comfortable with what x squared looks like? Yes? Little parabola like this. And it actually starts out at the origin here, goes up like this, and it goes up like that. That's what that would look like, right? And then we have the other function, 2x. Are we comfortable with what this looks like? It's a line. Agreed? And it has a slope of 2. And it goes through the origin. The y-intercept is 0, so it's going to go like this. So far, okay? Now, this information right here tells us that we're only supposed to draw x squared if our x values are smaller than or equal to 1. That means to the left of 1, right? So when I go back and look at this parabola, if I go to 1 on the x-axis, go up to this function, if I plug 1 in, I get a solid dot on the parabola. Why? Can I plug 1 into this function? Yes, and when I do, it plugs into this, right? Because of a little bar underneath that. So if I plug in 1 here, I get 1 squared, which is 1. 1, 1. Now, everything to the right of that parabola, I would erase, because I'm only supposed to have the parabola to the left of 1. Make sense? Now, what about the red one? The red one is to the right of 1, Yes? And so when I come over here to 1 and look up, I'm supposed to erase this stuff to the left so that my line only goes this way like that. Now, are we supposed to plug 1 into this function? Like if I plug in 1, does it go into this one? No. But just for the sake of us trying to figure out what's happening here, what would happen if we take a number that's really close to 1 and plug it in here? What would we get an answer? I mean, what would our answer be really close to? 2, right? We'd plug in 1 in here, we'd get something like 2. So that's why this is higher. I'm not allowed to plug it in, so I should have a little circle there, and that should be up here at 2. Does that picture make sense, like how I constructed that out of this? Okay, so right now, when you look at this, if you look to the left of 1, is this continuous to the left of 1? Right? Yes, you can draw it without picking up your pencil. To the right of 1, is it continuous? Just to the right? Yes, you can draw it without picking up your pencil. The only problem you ever have is at 1, right? Where this actually switches from one function to another, when that switch takes place, you have the potential to have a break in the graph, don't you? And so the only realistic question that can be asked in a problem like this is this function continuous at x equals 1? That's the question. Does that make sense? That to the left it's a parabola. Parabolas I can draw without picking up my pencil. To the right of 1 it's a line, and I can draw that without picking up my pencil. The only question is where they come together, can I draw it without picking up my pencil? And the answer is going to be what? No, but how would we know that without the graph? How would we know that without the graph? All right, so we're about to do something, and it's one of those issues where you've just got to really kind of understand what the definition is, all right? All right, so we're going to act like we don't know what it looks like, all right? Act like you never saw that graph. The question being asked is whether or not this function is continuous at 1. That right there means that we want to know, this is our solution here, we want to know if the limit as x approaches what? 1 of the function, is that equal to what? F of 1. Okay, now I wrote the definition of continuity at a point on the board just a second ago. I wrote limit x approaches a of f of x equals f of a. Means as we approached a, that limit needs to be equal to the function's value at a. Right? So if I'm saying is this function continuous at 1, it means does the limit as we approach 1 equal the function's value at 1? And this is the question. I mean, is that true or not? Right? Okay, so let's go about this and let's try and figure it out. All right? Let's try and figure out what's going on here. Now what I'm going to do is I'm going to work like left side and right side down, and I'm going to see if they hold, if the equation holds. Now the easier one to do is this one. So I'm going to say equals, this is still a question, are these equal? What is f of 1? So if I ask you to plug 1 into that function, what would you give me? 1. Because you're doing 1 in here, right? 1 goes there, 1 squared is 1. So you know the right side of this is 1. Okay? The only thing left to resolve is this. But remember that if it doesn't have the plus or minus here, that means it's both, isn't it? It's both of them, plus and minus. So what I'm going to do is on this side, do a little scratch work. I'm going to check what the limit as x approaches 2 from the left of this function is. And then the other thing I'm going to do is I'm going to check what the limit as x approaches 2 from the right of this function is. Okay? Do you understand what I'm doing? I need to know what this limit is. This limit doesn't have plus or minus, which means it's both, so I'm going to check both. Pardon? It's 1. Why did I put 2? Monday, Tuesday, whatever day it is. No excuses, okay? Thank you for catching that. Limit x approaches 1 from the left, 1 from the right. Okay. Let's start with this one. What is the limit as x approaches 1 from the left? Now, I had a calculus student in my office yesterday that was having trouble with this concept. So let's see how y'all do with this. I'm supposed to try this limit. I'm going to try and do like a direct substitution. I'm going to try and just plug 1 into the function. The problem is, which piece of the function am I going to plug it into? The top one or the bottom one? Why the top?
Because it's 1 equals.
Because I'm to the left of 1, right? If I'm to the left of 1 on a number line, I'm smaller than 1, which means I have to be here, right? This is smaller than 1, so I'm going to be plugging it into x squared. So I'm going to replace f of x with x squared because I am to the left of 1. And now just plug 1 in. What is 1 squared? 1? Okay. Y'all okay with that? So that doesn't tell me the answer to this yet, right? So far, one side of the limit is going to 1. Now, let's check the other side. If we now approach 1 from the right, what's the function we're going to use? So I'm going to write limit x approaches 1 from the right. What function am I going to plug in there?
2x?
This time the 2x, because we're approaching 1 from the right side, which is over here. We are bigger than 1, which means you must be using this part. So I plug 2x in here, and then this is 2. Ah, and guess what? These two are not the same, right? And since these two don't match, what is this limit equal to? DNE does not exist. And does not exist is not the same as 1, right? And since these don't match, the answer is no. It's not continuous. That's quite a bit of work involved there, right? But that's what you have to do. We'll do another one. And change it. Change the problem here. May I erase? Okay. Let's change this to 4x minus 3. If x is this time less than, just less than 2. And then, bless you, x squared plus 1 if x is greater than or equal to 2. So everyone got that down? I'm about to ask you whether or not this function is continuous at a value. What value do you think I'm going to ask? 2. Because that's the only really interesting place on this, right? So 2 is where I'm going to be asking. And let's just talk about what these functions would look like. If I graph that, what would that be? Straight line. That should be continuous, shouldn't it? Okay. And then what about x squared plus 1? What's that if I graph it? It's a parabola, and that's nice and continuous, isn't it? So again, this comes down to whether or not, where you bring them together, whether or not they're gonna line up or not. Does that make sense? So what I'm gonna do is go to the definition right now. What I want to know is the limit as x approaches 2 of this function equal to what? F of 2. That's what I want to know, right? Is that equal? Are those two things equal? Which side of that equation, because I'm going to work it left and right, which side of that equation is the easy part? The right side, right? So what is f of 2? 5. Man, where are you getting that from? Where are you plugging 2 in? You're going into the bottom one because it has the equal bar on it right there. You're going to plug 2 into this. 2 squared plus 1 is 5. So we're getting 5 on the right. Everyone good? Question, is this equal? So what am I going to need to do to figure out this limit? I need to go check both the left and right hand limits to see whether or not they match. So let's try the limit as x approaches 2 from the left of the function, and let's check the limit as x approaches 2 from the right of this function. And when I do the first one, I need to replace f of x with something. So what am I going to replace f of x with when I am approaching 2 from the left? The top one. And what's that going to be? 4x minus 3, right? I plug that in here. Are there any questions on why I'm doing this piece? Everyone's clear on that? Okay. So what happens if I plug in 2 into this? It comes out to be 5. Okay. I'm actually really liking this right now because this was 5 over here, wasn't it? And from one side, it's 5. I just need this one to be 5 also, and I'm done. And it will be continuous. Let's see if it is. So when I do limit from the right, I'm going to use the other piece, right? Which was the x squared plus 1. And we already did that. Like, that's kind of what we did over here. We just plugged in 2. So that's going to be 5 also. These two match. And so that's 5. And that checks. Is this continuous at 2? Yes. Questions? All right, who's going to tell me what our answer would have been to this question if these would have both turned out to be 4? If this was 4 and this was 4, what would our answer to this question be? No. And it would be because even though these are the same, this would have been 4 and that wouldn't have equaled 5. So that it would have not been continuous. The limit would have existed, but it wouldn't have matched the function's value. We good? Questions? All right. So in your homework, you've got to do 3 of these. I think I should probably give you just one more, and we'll go a little faster through this one. But it's a little different than the ones I just put up there. So how about this? Give you another function. All right, this is a piecewise function. It has 3 pieces to it. Oh, that was supposed to be -1 right there. I apologize. -1 right here. So the function is that if I am to the left of -1, I'm going to draw this line, right? If I am to the right of -1, I'm going to draw this line. Yes? And if I'm at -1, I'm going to draw this point. See, because this is telling you what to do exactly at -1. Exactly at -1, you plug in 1. You plug in -1, but it spits out 1. Yes?
Would it just be a point?
It would just be a point.
Okay.
Yep.
Would it be like continuous?
Well, that's if it was like, if this said like x is bigger than -1, then it would be a flat line. But because it's only happening at a single point, it's going to spit out a single point. All right, so I'm going to be asking you if this is continuous at -1. Is f continuous at x equals -1? That's the question. So we want, or we're asking ourselves, is, okay, and let's see. Okay, Google. Random number between, oh, whoa, that didn't work. Random number between 1 and 26.
Opening webpage.
Whoa, what happened? Ooh, Caitlin. Where's Caitlin? Is Caitlin here? No, Caitlin. Pierce? All right, Pierce. My question to you right now is for you to tell me what it is that I am trying to check here. Like I'm saying, is what?
So you would check the limit of -1.
As x goes to -1. Okay.
Right.
Okay, I think you're getting ahead of where I think you know what to do, but I'm saying this line right here should be, we're asking ourselves the question, is the limit as x approaches -1, right?
The limit of x approaching -1 is equal to
Uh-huh.
the function
At
at -1.
good. That's it, right there. That's what we need to check. Is that true? All right? Now, the easier part of this is the right side. So, Emmanuel, what's the right side of this? Okay, it's the middle one, right? So what is that value? 1, okay? And then to do this, we need to go check 2 limits, right? Okay, so let's do them. Do them quick. Limit, I'm going to go limit x approaches -1 from the left, and the limit as x approaches -1 from the right. Now, to save myself a little bit of time, what function goes into this limit? First function, because I'm less than -1, so x plus 2. And then which one goes into this one?
4 minus 2.
The 4 minus 2x, the bottom one. And what are these limits respectively? If I plug -1 in here, careful. Why did I put an x there? My fault. What do I get when I plug in -1 right here? I get -1 plus 2, that's 1, right? And then if I plug in -1 right here, be careful.
It's gonna be 2.
It'll be 4 plus 4, well, this is -1, right? So that's negative, so that's going to become positive 2. 4 plus 2 is 6. So what does that mean? That limit doesn't exist. Is it continuous? No, it's not. And we're done. All right. Let's move on. We're still in this section, but there's a couple of more things. You think you can handle some homework like that? You think you can envision seeing that on a test and being able to do this? On the test, when I ask you this question, I don't want to see like yes, no, without any sort of work, okay? I need to see you using the definition of the continuity definition to get to the result. All right, let's discuss continuity of common functions. One, all lines and quadratics and polynomials are continuous everywhere. So if I say, hey, draw a line, just draw me a line, you can be guaranteed that there's going to be no breaks or jumps or gaps or anything in that line. It's going to be continuous everywhere. Just a standard line, right? Y equals mx plus b. If I ask you to draw a parabola, you're going to draw that parabola. It's going to be nice and continuous, right? Any polynomial function, those are the ones that kind of look wavy. Those are all continuous functions. Now, the next type of function that we may deal with is rational functions. Are continuous on their domains. How many of you were ever taught I before E except after C? Anyone ever taught that in school? Is this spelled right?
Yes.
Why is it? It's not I before E except after C?
That is right. That's right.
But what about the rule I before E except
It's not
after?
always right.
It's not always right. See, that's why I'm a math major. Because when I was in English, I did not like that. So here's a rule, but not always true. That's kind of like my dad told me when I was a kid that, you know, when you're driving, you see the stop signs. Oops, that's a horrible stop sign. It says stop, right? He said that the stop signs that have white borders around the edges are optional. That's what he told me. I was like, what? And he was trying to make the point, like, you can't have a rule that sometimes has exceptions, then it's not really a rule, so. What's that?
The brackets I just asked you about earlier.
Well, okay, so the brackets, that's a very good question. Okay, because both of them are correct. Okay, the bracket being there is not a mistake. The parenthesis being there is not a mistake. They're both acceptable answers. So it's not like I'm giving you an exception. When we talk about continuity, and it happens with other parts of math where you leave the endpoint off, it's okay. I don't know, I mean, I'm not making an exception, I'm just saying for certain continuity, for intervals where you're increasing and decreasing, things like that, the point doesn't matter. Okay, so rational functions are continuous on their domains. Let me give you an example of a rational function, because these are a little bit less intuitive. Yeah, these are the ones that have asymptotes. So here's an example of a rational function. The numerator is a line, right? And you should be able to draw that without picking up your pencil. But the problem is you've got that down there also. So when you graph this, this is no longer a line. And so is this continuous? The answer is yes, everywhere except where it's undefined. So if I graph this, which I'm not going to get into the details of the graph of this, but 1, 2, 3. We are going to have a problem at 3, aren't we? Because it's undefined at 3. We get division by 0. However, the graph would look like this. It would go like this. And on this side at -2, it would go like this. That's what this graph looks like, okay? This is saying that all rational functions are continuous everywhere except where they might be undefined. So if I'm looking at this here, it's undefined at 3. But if I look over here, this is nice and continuous. And if I look over here, this is nice and continuous. Make sense? All right. All right, that's all we need. Root functions. Sorry, root functions are continuous also. 3. Root functions. Are continuous. I'm just going to put that continuous on domains. And I'll give you an example of this one. F of x equals the square root of x. if we graphed the square root of x, that's what it would look like. That's the graph of this function. Square root of 0 is 0. Square root of 1 is 1. Square root of 4 is 2. So you could graph this, but you can't put negative numbers in here, right? So the graph only exists over here. And if you draw this, it's going to be nice. You don't have to pick up your pencil. Understand? Okay. Now, why is this important? And like I said in the beginning of class, oh my gosh, we only have 15 minutes? Continuity is important, but it's this end result. And here's the big result, all right? Here it is. And I'm going to try and try to illustrate it with a picture. All right, let's say that I have some function f. F is continuous on some interval ab. And I'm going to put a and b over here. All right, so here's an interval ab, and I'm telling you that this function is continuous here, all right? Meaning you can draw it without picking up your pencil. Yes? I'm going to add some more conditions. F of a is greater than 0, and f of b is less than 0. What can you tell me for sure? F of a is greater than 0 means what? What does that mean? Visually, what does that mean? At a, it's where? Where's the graph? If I were to ask you to draw a point, which side? Down here or up here? It's got to be up here. Why? Because I said it had to be greater than 0, right? So when I plug in a, I get a positive number. And this says when I plug in b, I get a what? Negative number. Okay. If this was given, what can I say? What is a major conclusion of this? What can you tell me has to happen to the function somewhere between a and b? Has to what? Has to cross the x-axis. Doesn't it?
Yes.
I must, if I've got to go from here to here without picking my pencil up, I must cross through here, must I? Right? So that means when I go like this, doesn't matter how I draw it, there's got to be somewhere, right? Somewhere in here. Now, I don't know exactly where it is, but I'm guaranteed it's there, right? I'm guaranteed it's there. The conclusion of this is there must exist a C, all right, in the interval AB such that f of C is what? What's the function's value at C? 0. In other words, we have an x-intercept, don't we? We have an x-intercept. You following me? You sure?
But it doesn't have, like, what if the function was above? It doesn't have to be an x-intercept.
If the function was above?
Yeah, like,
Yeah, but okay, I gave you these conditions, right? I gave you these conditions. So if I'm telling you, hey, look, you have to draw your function without picking up your pencil. That's what that line says. And then I tell you that when you start to draw it, you have to be above the x-axis. And when you end drawing it, you have to be below the x-axis. The conclusion is that there's got to be some point in between A and B where I must cross the x-axis. Right? Now, this may not seem like a big deal.